Hello everyone, my name is Quentin Wu, and today I would like to share with you our recent work on how externally imposed shear stress interacts with internally generated active stress in microtubule kinesin active fluids, and how this interaction depends on confinement geometry. And this work is a collaboration with Dr. Thomas Powers and Dr. Robert Pelkovic at Brown University. My group primarily carried out experiments and data analysis, while Tom and Bob's group focused on the theoretical modeling and numerical simulations. And this research was also supported by the National Science Foundation, with additional support from the Brandeis Mercek. So, our group focuses on a specific class of active matter called microtubule kinesin active fluids. And in this system, there are three main components. The first component is microtubules, shown here as green filamentous rods in the schematic. And these are rigid rod-like protein filaments. And the second component is depleting polymers, illustrated here as blue spheres. And these polymers generate an effective osmotic pressure that drives nearby microtubules together, causing them to bundle. And once microtubules are bundled, the third component comes into play, the kinesin motor proteins, or more specifically, kinesin motor dimers. And in cells, kinesins walk along microtubules while transporting cargo. Each step they take consumes one ATP molecule, converting ATP to ADP. So ATP is the fuel that powers motor motion. And when kinesin motors are dimerized, it can bridge pairs of anti-parallel microtubules within the bundle. And as the motors walk, they force these anti-parallel filaments to slide apart, generating interfilament sliding. This interfilament sliding has been directly observed in the lab. In the video shown here, you can see that when anti-parallel microtubules come together, they are immediately driven to slide apart. This sliding motion is a fundamental microscopic mechanism underlying activity in our system. Collectively, many of these sliding events cause microtubule bundles to undergo repeated cycles of extension, buckling, and healing. And on larger length scales, the microtubules form a percolating, constantly reconfiguring network that continuously stirs the surrounding solvent. And to visualize the resulting fluid motion, we add fluorescent tracer particles, shown here in red, and track their trajectories. And these trajectories reveal disordered, turbulence-like chaotic flows. In our previous work, we showed that these chaotic flows can be used to enhance micromixing. However, in this video, we'll focus on a different question. We ask how this intrinsically chaotic active flow responds when we apply an external mechanical perturbation. To introduce a well-controlled mechanical perturbation, we consider a cavity flow system. But what is a cavity flow system? Well, in classical fluid dynamics, a cavity flow refers to a system where a fluid is confined within a square boundary, and one side of that boundary moves at a constant velocity. So as shown in this video, when water is confined in a square tank and shared by a moving belt at the top, the fluid organizes itself into a large tank-sized circulation, which is a single dominant vortex filling the entire cavity. And this example operates at macroscopic meter-scale size. In our experiments, we apply the same idea by shrinking it down by several orders of magnitude and reproduce a millimeter-scale cavity flow. And this system allows us to ask, how does an active fluid that already generates its own chaotic flow respond to this kind of externally imposed shear? So how do we create this millimeter scale cavity flow system? Here is a schematic of our experimental setup. We use 3D printing to fabricate a mini fluidic device with a square cavity at its center. This central square region is where the active fluid is confined and where we study the flow. One side of the cavity is open and connected to a narrow channel that contains a thread. And by translating this thread, we impose a controlled shear stress on the fluid inside the cavity, effectively creating a cavity flow system at a millimeter scale. And the image on the right shows a photograph of the experimental setup. This thread is driven by the motor whose speed is computer controlled, allowing us to tune the driving speed and therefore the magnitude of the applied shear. And with this setup in hand, let's look at how the active fluid behaves under various external driving conditions. Here, I'm showing 3 videos of tracer particle motion inside the cavity, corresponding to low, intermediate, and high thread speeds. On the left, the thread speed is very small, about 8 microns per second. In this case, the flow looks essentially the same as undriven active fluid. The motion is chaotic and turbulence-like. And externally imposed driving does not significantly influence the bulk flow. In the middle panel, the thread speed is increased to 58 microns per second. And here we begin to see a mixed response. Part of flow is influenced by the driving, while chaotic active flows persist elsewhere in the cavity. So in other words, driven flow and active fluid-driven chaotic flow coexist. Finally, on the right, the thread speed is much higher, about 430 microns per second. And in this region, the active fluid-driven chaotic flows are suppressed, and the flow pattern becomes dominated by the external driving. The system now resembles a conventional cavity flow, with a large-scale circulation filling the cavity. I want to emphasize that what you see here are only the tracer particles. The underlying activity is still generated by extensile microtubule bundles in the background. However, by tracking the tracer motion, we can reconstruct the flow field and quantitatively characterize how the system transitions from activity-dominated to externally driven behavior. To move beyond qualitative observations, we next analyze these tracer motions and reconstruct velocity fields and vorticity maps. Here are the instantaneous velocity fields and vorticity maps reconstructed from the PIV analysis of the tracer motion. And as expected, these flow maps showed a clear evolution. At low driving, the flow is dominated by many small disordered vortices, while at the high driving, the flow organizes into a single cavity-scale circulation. But to go beyond visual inspection, we need a quantitative way to characterize the flow structure and extract the length scale from these patterns. To quantify these flow patterns, we analyzed the normalized equal time velocity correlation function, which measures how strongly the flow velocities at 2 points in a cavity are correlated as a function of the separation distance. And intuitively, these tell us over what length scale the flow remains coherent. From this correlation function, we extract a correlation length, which represents the typical size of flow structures in the system. We repeat this analysis for different thread speeds and plot the correlation length as a function of the driving speed. For the active fluid, the correlation length is about 200 microns when the thread speed is near 0, reflecting the intrinsic voltage size generated by internal activity. And as the thread speed increases, the correlation length grows almost linearly, indicating that the externally imposed shear progressively organizes the flow. And beyond the thread speed of roughly 120 microns per second, the correlation length saturates and plateaus at around 600 microns. This saturation suggests that above a certain driving strength, the flow is no longer set by internal activity, but instead becomes dominated by the external shear. And to make this point clearer, here we compare the active fluid with passive water under similar driving conditions. And on the bottom left, I'm showing 3 videos of water driven at different thread speeds. In all cases, the flow pattern is essentially the same, which is a cavity scale circulation. Increasing the thread speed only changes how fast the flow moves, not its structure. This behavior is very different from what we observe in the active fluid, which are shown in the panels above. There, the flow structure evolves dramatically with increasing thread speed, reflecting the competition between externally imposed shear and internally generated active stresses. This difference is also captured quantitatively in the plot on the right. The blue dots show the correlation length measured in water, which remains nearly constant at around 600 microns across the entire range of the thread speeds. This length scale is set by the system size, since water has no internal active stress. In contrast, the active fluid initially exhibits a much smaller correlation length, but as the thread speed increases, its correlation length grows and eventually converges to the same value as water. Once the thread speed exceeds about 120 microns per second. This convergence indicates that above this driving strength, the external shear overwhelms the internal active stress, and the system dynamics become dominated by the imposed boundary condition. At this point, a natural question arises. Why does this transition occur around 120 microns per second? This number is not expected to be universal. It depends on geometry, length scales, and fluid properties. So, what really matters is not the thread speed itself, but the shear stress imposed on the system. So next, we estimate the magnitude of external shear stress corresponding to a thread speed of 120 microns per second, and compare it with known values of active stress in microtubule kinesin systems. To do this, instead of focusing on correlation lengths, we look directly at the flow pattern at its driving speed. Here, we overlay about 30 seconds of tracer images, which reveal a dominant cavity scale vortex induced by the moving thread. This vortex allows us to estimate the characteristic velocity gradient in the system. Near the moving boundary, the flow speed is set by the thread speed, which is about 120 microns per second, and it decreases to nearly zero toward the center of the vortex over a distance of roughly 360 microns. And using the definition of viscous shear stress as viscosity times the velocity gradient, and taking the viscosity measured in our previous work, we obtain an estimated external shear stress of approximately 1.5 MPa. Note that this value corresponds to the driving strength at which we observe the transition from active-dominated to shear-dominated flow. So this suggests that at this point, the externally imposed shear stress should be comparable in magnitude to internal active stress generated by microtubule kinesin network. As such, we estimate the active stress in our system to be on the order of 1.5 MPa, which is consistent with existing estimate in the literature, typically ranging from 1 to 10 MPa. So, at this point, everything seems consistent. We estimate the external shear stress at transition, and when that shear stress becomes comparable to internal active stress, we observe a qualitative change in the flow. This allows us to estimate the active stress in our system, and that estimate agrees well with the value reported in the literature. However, there is an important subtlety. When we look more closely at prior work, we notice that this same stress scale also appears in the studies of microtubule networks subject to external loading. In particular, in previous rheological experiments done by Gyakten et al., microtubule kinesin networks were coupled to a rheometer, and those studies showed that when the externally applied stress exceeded roughly 2.2 MPa, the network underwent mechanical breakdown. And this raises an alternative explanation for the transition we observe, meaning that it's a change in the flow behavior driven by the hydrodynamic competition between external shear stress and internal active stress, or instead, is it caused by the structural failure of microtubule network under external driving? Distinguishing between these two possibilities is crucial because they imply very different physical mechanisms. So next, we'll examine the microtubule network structure under driving. To test whether the transition is caused by the network rupture, we examine the microtubule network structure near the moving boundary. What I'm showing here are the confocal fluorescent images of microtubule network taken with and without external driving. On the left, the thread is stationary, and as expected, microtubules form a percolating dynamic network whose structure continuously self-rearranges due to internal activity. And this is the characteristic behavior of a microtubule kinesin system. On the right, the thread is moving at a speed above the transition value of 120 microns per second. And in this case, we see that microtubules near the boundary are dragged along the thread motion, and the network becomes more aligned with the imposed shear direction. However, while the external driving influences the network structure and induces alignment, we do not observe network rupture or breakdown in these confocal images. These observations suggest that the transition in the flow behavior is not driven by mechanical failure of the microtubule network. So our hypothesis is falsified. And this raises the question of whether the observed transition was mainly the consequence of competition between external shear stress and internal active stress without involving network breaking. To address this question, we developed a numerical simulation designed to isolate the competition between externally imposed shear stress and internally generated active stress. The model describes the system using two coupled fields, a flow field V, which captures the fluid motion, and a nematic order field Q, which represents the local alignment and internal structure of microtubule network. These two fields are coupled and evolve together. Or more explicitly, in our model, the nematic order generates active stress that drives fluid flow, and the resulting flow in turn reorients and reorganizes the nematic structure that generates the active stress. External shear enters the model solely through the boundary conditions, by imposing motion at the boundary similar to the moving thread in the experiment. To quantify the competition between external and internal stresses, we define a dimensionless stress ratio, which we call lambda. When lambda is less than 1, internal active stress dominates. When lambda is greater than 1, externally imposed shear dominates. Before introducing activity, we first validate the model using passive water. As shown here, the simulation reproduces a conventional cavity flow pattern for water, confirming that the model captures the essential cavity flow physics. With this validation in hand, we then turn on active stress and examine how the flow behavior changes as we vary the stress ratio. Now, let's look at the flow fields obtained from numerical simulations. On the left, there is no externally imposed shear. In this case, the flow is solely driven by internal active stress. And we observe chaotic, turbulence-like flow patterns, similar to those seen in undriven active fluids in experiments. In the middle panel, we introduce a moderate external shear. Here, we observe that driven flow begins to emerge near the boundary, while chaotic active flows persist in the bulk. In other words, externally driven flow and the active stress-driven chaotic flow coexist. On the right, the external shear is strong. In this regime, the active stress-driven fluctuations are largely suppressed, and the flow organizes into a cavity-scale circulation dominated by the imposed boundary motion. Qualitatively, these simulated flow patterns closely mirror what we observe experimentally, even though the model does not include any network breaking or rupture mechanisms. But to better quantitatively compare the simulation results with experiments, we performed a similar velocity correlation analysis and extract a correlation length. Here, we plot the correlation length as a function of the stress ratio lambda. We find that the correlation length increases as external shear becomes stronger, and then saturates once the external imposed stress dominates the active stress. This trend is qualitatively consistent with what we measured experimentally. We also note that in the simulation, the transition occurs around lambda equal to 1, meaning that at the transition, the externally imposed shear stress and internally generated active stress are comparable in magnitude. This is consistent with our experimental stress estimate, where we interpreted the transition as when external stress and active stress become comparable. Taken together, the experiments and simulations support a clear conclusion. The kinematic transition in the cavity is governed by the stress competition between external shear and internal active stress, without requiring network rupture. However, the cavity geometry is a relatively open, slab-like confinement. Once we drive the boundary, the imposed shear can penetrate into the bulk and directly compete with the active stresses throughout the domain. This raises another question. How does the transmission of external stress change when the confinement geometry is no longer open, but instead more constrained or ring-like? Can confinement geometry suppress or redirect externally imposed stress in a way that alters the responses of the active fluid? To address this question, we confine the active fluid in a toroidal geometry. From our previous studies, we know that when microtubule kinesin active fluids are confined in a closed loop-like geometry, they can spontaneously develop coherent river-like circulating flows. To control the direction of this spontaneous circulation, we decorate the outer boundary with asymmetric teeth. These teeth do not generate flow, but they bias the circulation direction. As a result, in the absence of external driving, the active fluid develops a counterclockwise coherent flow. To apply external driving, we replace a small section of toroidal outer boundary with a channel containing a movable thread, allowing us to impose shear locally in a toroidal channel. And when the thread starts to move, the externally imposed shear begins to influence the flow. And over time, the circulation reverses the direction, transitioning from counterclockwise to clockwise flow. Now, when we stop the external driving and allow the system to relax, something interesting happens. After some time, the flow spontaneously reverses again, returning to the original counterclockwise direction. This indicates that the boundary teeth continue to bias the flow direction even after the driving is removed, and that the system relaxes back to the geometry selected state once the external forcing is no longer present. Okay, so far we have seen from the movies that external driving can reverse the direction of coherent circulation in a toroidal geometry, and that the system can relax back to the geometry selected state once the driving is removed. And to go beyond visual inspection, we now want to quantify how the active fluid responds to external driving and how this response evolves in time. Here, we use PIV to analyze tracer motion and reconstruct time average flow fields before driving, during driving, and after driving. Before driving, the flow shows a stable counterclockwise circulation. During driving, the circulation reverses and becomes clockwise. After the driving is stopped, the flow relaxes back to counterclockwise circulation. While these flow maps show the change in circulation direction, they also reveal that the flow remains coherent throughout all three stages. This means that unlike in a cavities geometry, correlation length is no longer an informative metric for characterizing the response of the system. To characterize the response in a system, we instead focus on the direction and stability of the coherent circulation. And to achieve this, we define the circulation order parameter, ranging between -1 and +1. Circulation order parameter equals +1 for perfect counterclockwise circulation, -1 for perfect clockwise circulation, and 0 for disordered or chaotic flow. This order parameter allows us to track how the global circulation responds to external driving as a function of time. Here, we plot the circulation order parameter as a function of time. Before driving, the order parameter is positive, indicating persistent counterclockwise circulation. When external driving is applied, the order parameter rapidly decreases and reaches a negative value corresponding to flow reversal. And after driving is stopped, the order parameter slowly relaxes back to its original positive value as the boundary teeth reassert directional bias. These time-dependent behaviors reveal how the active fluid responds dynamically to external stress. To quantify this dynamical response, We focus on how fast the circulation reverses after the driving is turned down. We measure the initial rate of the change in the order parameter immediately after driving begins, fit it to the linear slope, and define the magnitude of this slope as a reversal rate lambda. We repeat this analysis across different driving speeds and toroidal boundaries with different number of teeth, and plot the resulting reversal rate as a function of thread speed. Here, we observe that reversal rate is largely independent of number of teeth. Our data from 1, 2, and 3 tooth geometries collapse onto the same curve, indicating that the teeth bias the direction, but do not significantly influence the reversal dynamics. We also find out that reversal only occurs when the thread speed exceeds a threshold of approximately 30 microns per second. Below this value, reversal does not happen. We then estimate the corresponding shear stress given a value on the order of 1 millipascal, which is comparable to the stress threshold observed in a slab-like cavity geometry. And above this threshold, the reversal rate increases approximately linearly with the driving speed, even up to the highest driving speeds accessible experimentally. This linear increase is consistent with the fact that these data lie in a region where externally imposed shear stress exceeds the internal active stress. So stronger shear drives faster reversal. In a slab-like cavity geometry, driving at this stress scale leads to a direct entrainment of the bulk flow by the external shear. In that region, the flow becomes indistinguishable from that of passive water. If the same direct entrainment mechanism were at work in a toroidal geometry, we would expect the reversal dynamics of active fluid to be comparable to those of water. However, this is not what we observe. In water, flow reversal under similar driving conditions occur within roughly 30 seconds. Corresponding to reversal rates, they are an order of magnitude larger than those measured in the active fluid under similar driving conditions. This quantitative mismatch suggests that, unlike in a slab-like cavity geometry, flow reversal in a toroidal geometry is not governed by simple direct entrainment of the bulk flow. Then, if this is the case, then what mechanism is responsible for the flow reversal in a toroidal geometry? To understand why the reversal dynamics differ so much from water, we examine the time average flow fields in a toroidal system during driving. What we observe is that the external driving mainly generates a localized mini-cavity flow near the driving entrance. This localization is expected since the central hole of a toroid prevents the externally imposed shear from directly entraining the entire bulk flow. This suggests that the global reversal may not be driven by the direct entrainment, but instead by how the active fluid responds to this localized shear perturbation. To test this, we designed a system of two connected toroids. Only the upper toroid is directly driven by the moving thread. The lower toroid is undriven and contains boundary teeth to bias spontaneous circulation. Then, we compare response of the second toroid in active fluid to water. So, in the active fluid case, before driving, the two toroids exhibit biased spontaneous circulation with opposite directions. And When driving begins, the upper toroid reverses first, followed by the lower undriven toroid. So, for the active fluid case, the lower toroid is reversed. Now, let's compare this with water under the similar driving conditions. In water, external driving generates mostly a localized mini-cavity flow near the entrance of the upper toroid, while the second toroid remains quiescent throughout the experiment. This stands in contrast to active fluid system. And this contrast shows that in active fluid case, the flow reversal in the second toroid arises from stress cooperation between externally imposed shear and internally generated active stress, rather than from direct entrainment. Let us summarize what we learned today. In this work, we studied how microtubule kinesin active fluids respond to external driving in 3 different confinement geometries: slab-like cavities, toroidal confinement, and connected toroids. While these experiments may look very different, together they reveal a unified picture of how active fluids respond to external stress. First, across both slab-like and toroidal geometries, we identify a common stress threshold for response. We find that the active fluid only responds appreciably when the externally imposed shear stress becomes comparable to or exceeds the internally generated active stress. In our system, this active stress is on the order of 1.5 MPa. Second, once this stress threshold is exceeded, the nature of the response depends critically on confinement geometry. In slab-like confinement, external shear can directly penetrate the bulk. In this case, the response is governed by stress competition between external shear stress and internal active stress, leading to a kinematic transition that we reproduce using continuum simulations. In contrast, in ring-like geometries such as toroids and connected toroids, external shear is localized near the driving entrance, forming a mini-cavity flow. Here, the global response of the system arises not from direct entrainment, but from stress cooperation, where internally generated active stress amplifies and transmits the effect of localized external perturbations. Taken together, our results show that eliciting and controlling responses in active fluids requires more than simply exceeding a stress threshold. The topology and geometry of confinement play a decisive role in determining whether active fluid responds through stress competition or stress cooperation. More broadly, this work highlights that when designing microfluid systems that incorporate active matter, one must consider not only the magnitude of external forcing, but also the geometric and topological constraints imposed on the active fluids. These are what we learned today. If you are interested in more details such as additional flow analysis and quantitative metrics, you are welcome to check out our full publication of this work listed in the video description. And of course, if you have any questions or suggestions, feel free to reach out to us. Thank you for watching.